Okay, good afternoon. Just picking up where we have left off with exponents and logarithms. And I said from the test for review part one set, okay, to look into from the first page, numbers 9 through 12. And we have, in the case of number 9, okay, so we're looking at a logarithmic term. And again, we have just a plain log. And again, if you have just log, this will be in reference to a base 10 logarithm. And we have quite a few factors in the mix where we have, within the parentheses, we have 10 times u to the 3/4 times x to the 5th. And we have times the cubic root of z to the 4th minus 13. And we have all over, okay, the square of w plus 1 times y to the 2/3. Okay, and looking at expanding, and what I have done a little bit beforehand is to write the radical regarding the cubic root of z to the 4th minus 13 in terms of a non-integer exponent. So we have so we got a base 10 logarithm. So now we have in the rewrite, we have 10 times u to the 3/4 times x to the 5th. And we have times the quantity of z to the 4th minus 13 raised to the 1/3 power. And again, we have all over w plus 1 squared times y to the 2/3. And again, just looking at getting things going. And we have, if we just look at what is at the top, okay, so we have, in this case, we have 4 distinct factors. Okay, so we have base 10 logarithm of 10. And again, multiplication in the attachment implies addition whenever we are expanding into separate logarithmic terms. Okay, so you have plus the base 10 logarithm of u to the 3/4. And we have next, we have x to the 5th. So we're going to have a base 10 logarithm of x to the 5th. And we have with also z to the 4th minus 13 quantity to the 1/3 at the top. Okay, so as its own logarithmic term, okay, this is also going to be added. Now for the other factors, they are situated in the denominator. And we have division is going to imply subtracting. Okay, so we have for the base 10 logarithms with these two attachments, again, these will result as negative base 10 logarithmic terms. Okay, so we have minus the base 10 logarithm of w plus 1 to the 2nd. And we have minus the base 10 logarithm of y to the 2/3. Okay, and we have quite a long statement in the expansion. Okay, and just looking at what we have in the mix. Okay, so we have with log of 10, again, log is implicit notation for a base 10 logarithm. Okay, so you have with log, you're going to have base 10 logarithm of 10, and so just standalone 10, that's going to be 10 to the first. So this will go to 1. And for the powers, okay, those will be converted to coefficients. And see, that was to the 1/3 degree. There we go, in front of the log. Okay, so we have for the base 10 logarithm of 10, okay, that will go to 1. And we have plus 3/4 of the base 10 logarithm of u plus 5 times, okay, the base 10 logarithm of x. And we have plus 1/3 of the base 10 logarithm of z to the 4th minus 13. So again, z to the 4th, the z, the 4th degree, all that is going to stay in the attachment. And then we have minus 2 times the base 10 logarithm of the quantity of w plus 1. And finally, we have minus 2/3 of the base 10 logarithm of y. Okay, and so again, we have quite a few terms in the mix. Okay, so we've got 6 of these, and so again, reducing any exact terms, okay, to a constant where possible, okay, which was in the case the base 10 logarithm of 10 is equal to 1. Okay, again, we have for the rest of the terms converting from the powers that we had to coefficients. Okay, and so this will be the final form for what we have in this problem. Okay, now for what we have in the case of number 10, okay, and we're looking at writing what we have going from separate terms in the same logarithmic base to one combined term. And in the case of number 10, okay, so we have, in this one, so you have, so you got 2 times, okay, the base 5 logarithm of 10. And we have plus 3 times, okay, the base 5 logarithm of x. And we have minus 2 times the base 5 logarithm of y. Okay. Again, when we expanded, we had gone from exponents to coefficients, and we're going to do it the other way around. So we're going to have at this juncture, okay, so we have the base 5 logarithm of 10 to the second, and we have plus the base 5 logarithm of x to the third, and we have minus, okay, the base 5 logarithm of y squared. Okay, and looking at clustering the attachments into forming a single base 5 logarithmic term. And again, addition is going to imply multiplication when consolidating, whereas subtraction is going to imply division. Okay, so we have also got 10 squared from a positive base 5 logarithmic term. Okay, so that's going to go to the top. Likewise, x cubed stems from a positive base 5 log term, so that's going to go to the top. And with y squared attached to a negative base 5 logarithmic term, that's going to go on the bottom. And I would regard that as a complete answer, but just adjusting what we have with the constant 10, okay, to the second, and we have 10 squared, okay, so this will be 100 x cubed all over y to the second. All right, now in the case of what we have regarding number 11, okay, and we have for this one, okay, we have just looking at putting together. And I'll tell you what I will do here. Okay, so just looking at, again, just for the adjustments. Okay, so you have 2 times, okay, the natural logarithm of u. Okay, so again, we have 2 is going to become an exponent. And next in line we have plus 3 times the natural logarithm of v. Okay, so 3 is going to become an exponent. And we have plus 1/2 of the natural logarithm. Okay, and we have the quantity of u plus v. And again, the coefficient 1/2 is going to be written as a power. And then we have minus 3/4 of the natural logarithm. Okay, and we have within the parentheses we have a trio whereupon we have w to the 4th plus y to the 5th minus z. And that 3/4 will be converted to an exponent as well. Okay, so looking at what we have. Okay, so we got the natural logarithm of u to the second, and we have plus the natural logarithm of v to the third, and we have plus the natural logarithm of u plus v, quantity, to the 1/2, and we have minus, okay, the natural logarithm. Again, we have this 3-term expression, and this will be to the 3/4 power, and putting together as a single natural logarithmic term. Okay, so we have with u to the second, okay, this stems from a positive natural logarithmic term. Okay, so this will go to the top. V to the third will do the same, and u plus v to the 1/2 likewise. And with the last term subtracted, okay, we're going to have this 3-term expression to the 3/4 power in the denominator. Okay, so just keeping the exponents throughout, including the non-integer ones. Okay, this can be your final result. And if there were any other way to write this, see, like going from non-integer exponent to radical, like if I wanted to display the radical, okay, we have as an alternate answer. Okay, so I can have u squared times v to the third, and for u plus v to the 1/2, this will be the same as the square root of u plus v. And we have for this 3-term expression to the 3/4 power, if I were to put this as a radical, again, the type of index number or the type of radical is going to be indicated by the denominator in the exponent. Okay, so this is going to be a 4th root, and it's going to be the 4th root of the cube of w to the 4th plus y to the 5th minus z. And that is another way of displaying your final result. All right, now for what we have in the case of number 12, okay, another little bit of a trick item, and we have for this one, okay, so we got in the case of 12, okay, so you have 12 times the base 5 logarithm, the cubic root of y minus 4, and we have plus 2 times the base 5 logarithm of the quantity of y squared plus 5, and we have minus 5 times the base 5 logarithm of the cubic root of y plus 5. Okay, and this is a little bit of a tricky item, and if I were to rewrite, say, the radicals in terms of non-integer exponents, okay, so I'm going to have 12 times, okay, the base 5 logarithm of the quantity of y minus 4 to the 1/3, and I have plus 2 times the base 5 logarithm, okay, and we have of the quantity of y squared plus 15, and again we have minus 5 times the base 5 logarithm, okay, and for the cubic root of y plus 5, again, this is going to be the quantity of y plus 5 to the 1/3. Okay, and so we have for this problem, okay, looking at how we're going to follow through on this one. Okay, so I got, if you notice, for the first and the last terms, I have the simultaneous appearance of a leading coefficient as well as a power, and those exponents are going to be affected. Okay, and so for what we have for this expression, okay, so I'm still going to, in their own right, convert these leading coefficients into exponents. And we have for the leadoff term, Okay, so I'm going to have the base 5 logarithm. What it's going to be, and just to kind of give you a visual, okay, so we have the base 5 logarithm, and we have of the quantity of y minus 4 to the 1/3, and this is going to be to the 12th power. Second term, we'll have the base 5 logarithm, and we have of the quantity. Okay, we have y squared plus 15, and that is going to be raised to the 2nd power. And we have with the third term, so we have minus, okay, the base 5 logarithm. And so we'll have y plus 5 to the 1/3, and having shifted the 5 in exponential position. So I'm going to have the quantity of y plus 5 to the 1/3 raised to the 5th. Okay, and so we have the first and the last terms. Okay, we have with the attachments. Okay, I'm going to apply the power property of the exponents. So we're going to have here the base 5 logarithm, and we're going to have y minus 4 to the 1/3 times 12 degree. And 1/3 of 12 is going to be 12/3, which is going to be 4. So we have y minus 4 raised to the 4th. And we're going to have plus the base 5 logarithm. Again, so we're going to have y squared plus 15 raised to the 2nd. And then we have minus, okay, the base 5 logarithm. And this is going to be of the quantity, so you have y plus 5. And with the power property, this will be to the 1/3 times 5 degree. So we're going to have the power to be at 5/3. And looking at consolidating as a single term in the logarithm base 5. Okay. So you have the base 5 logarithm. Okay, and with the first two terms being positive, these attachments will go in the numerator. Okay, so you have y minus 4 to the 4th. Then we have times, okay, and y squared plus 15, quantity squared. And with the last term being subtracted, okay, this attachment will go in the denominator. Okay, and so that would be a complete answer, and just another way that this could possibly be written. Okay, notice we have a non-integer exponent in the denominator, and this could be written in radical terms. Okay, so you have to the 5/3 power, and so if I wrote this in radical terms, I'm looking at the cubic root of what is going to be y plus 5 raised to the 5th power. This is just another way, okay, but this answer is a complete answer in its own right. Okay, now for what we have in the case of looking at what we have concerning exponential equations, okay, that will share a common base, and we have from the second page, and we have for item number 13, okay, so we're looking at whereupon 8 to the x plus 6 is equal to 4 raised to the x. So we're looking at solving for x. Okay, so you have, again, so you have 8 to the x plus 6. 8 to the x plus 6 is equal to 4 to the x. Okay, now, again, we can write this and solve for x. Okay, now, we have 8 to the x plus 6 is equal to 4 to the x. Okay, now 8 is a multiple of 4 once again, but it is not an integer power of 4. And working with integer powers and common bases. Okay, now for both 8 and 4, now you're going to have the common base to be at 2. And so if I rewrite both of these expressions in terms of base 2, now 8 is going to be 2 raised to the third. And for 8 to the x plus 6, okay, this would be 2 to the third raised to the x plus 6. For 4 to the x, now 4 is 2 squared. And 4 to the x would be 2 squared to the x. So I'll be multiplying the exponents again by the power property of exponents. So for 2, okay, this will be raised to the 3 times the quantity of x plus 6. Whereas for what we have on the right, okay, we have 2 raised to the 2 times x. Now we got single base 2 terms. And just taking what we have on the left upon distributing 3 over the quantity of x plus 6. So we have 2 raised to the 3x plus 18 is equal to 2 raised to the 2x. Now we got single base 2 terms. And so in terms of solving for x, okay, we can go ahead and set the powers equal to each other. Okay, so you have 3x plus 18 is equal to 2x. And I can join the x terms together. Now 2x is by itself. And if I move the 3x by subtracting on both sides, so I'm going to have that 18 is equal to negative x. And just changing the signs, going from negative to positive x. Okay, so it's going to turn out that the missing value x is equal to negative 18. All right, now where we have an exponential equation also that will share a common base, and we have with number 15. Okay, so here we have 1 over 1,000 to the x is equal to 10 to the 1 plus x. To the 1 plus x. Okay. Okay, so we have for this setup, okay, so we got the reciprocal of 1,000, okay, and in the case of what we have with 1,000 as well as 10, okay, there's going to be a common base with what we have concerning 10. Okay. So we have here, we have a common base with 10. Okay, so we have 1 over 1,000. Okay, so this is going to be 1 over 10 to the third. Is equal to 10 raised, okay, to the 1 plus x degree. Okay, so I got 1 over 10 third quantity to the x, and I have equal to 10 raised to the 1 plus x. Now, both terms in a way are in base 10, okay, but I want to get out of the fraction mode. Okay, so I got the reciprocal of 10 to the third. Okay, so just writing this directly in terms of base 10. Now the reciprocal of a base to a positive power is going to be that base to the negative power. So for 1 over 10 cubed, we have 10 to the negative 3. And so will again be to the x. And again, we have is equal to 10 raised to the 1 plus x power. And taking care of 10 to the negative 3 to the x. And we have with the power property of exponents. So you have 10 to the negative 3x is equal to 10 raised to the 1 plus x power. So we got single base 10 terms in direct fashion. And we can now set the powers equal to each other. Okay, so you have negative 3x is equal to 1 plus x. And again, combining the variable terms together. So I have negative 3x by itself, and that is going to be joined with the subtraction of x. So negative 3x minus x becomes negative 4x. And we have negative 4x is equal to 1. And it's going to turn out that for the value of x, this is going to be a negative fraction in this case. So we have negative 1/4. Okay, and we'll look into the business applications in just a moment. But with still on the pathway of working with exponential equations, in the case of working with what we have here. Okay, say if you have, I'm going to say just as an instance here, if I have, so like 8 to the x, and I'll say that I have times 4 to the x plus 1, and we have is equal to, let's say we have 16 to the x minus 2. Okay, say we have more than just one term on both sides. Okay, or I should say a situation where we have more than two terms separated by the equal sign. Okay, so we've got two terms on the left, one on the right. And looking at what we have here, we've got 8 to the x, 4 to the x plus 1, 16 to the x minus 2. And for these now, you're going to have a common base with the number 2. And for what we have with 8 to the x, now 8 is going to be 2 cubed. This will be to the x. Now for 4 to the x plus 1, now 4 is going to be 2 squared. Yeah, to the x plus 1. Now for 16 to the x minus 2. Okay, so you have 2 to the 4th raised to the x minus 2. And for 2 cubed to the x, okay, so we have 2 to the 3x. And for 2 squared to the x plus 1, so again we have with the power property. So I have 2 to the 2 times the quantity of x plus 1. And for what we have on the right, we have 2 to the 4 times all of x minus 2. And the reason I'm stressing the parentheses is that I have seen mistakes like 2 to the 2x plus 1 and 2 to the 4x minus 2 without the parentheses. And they just leave it as like 2x plus 1 and 4x minus 2, but without multiplying the constants by the number in front. So I just wanted to mention that as a safeguard from careless mistakes. So we got 2 to the 3x, and we have times 2 to what is going to be the 2x plus 2 degree. And we have is equal to 2 raised to the 4x minus 8. And if you notice, we have singular base 2 terms, but I want one base 2 term on each side. Okay, so I got 2 right here, and I can just consolidate into 1 again by taking the product property, which will be involving adding the exponents together. So we have 2 to the 3x plus 2x plus 2. I have is equal to 2 to the 4x minus 8. So we have 2 raised to the 5x plus 2. And that is equal to 2 raised to the 4x minus 8. So now I have single base 2 terms. And now I can set the powers equal to each other. Okay, so we got 2 sets of terms that are alike and on both sides. And what I'll do here is that I'll combine the x terms. So I'll take the smaller one, in this case 4x, from the larger. And I'll move the 2 over. So you got 4x from 5x. Okay, so this will yield x. And for the missing value x, we have negative 8 minus 2. And so this will come out to negative 10. All right. Okay, so just another case of what we have for exponential equations that will share a common base. All right. Now, for what we have in the case of, again, just going back to the interest problems, and we have for number 25, okay, and we have here for compound interest and future value. And we have for number 25, okay, and it says to find the future value of $3,000 invested at 10% compounded monthly after 6 years. And then in part B, okay, we have it to be compounded continuously after 6 years. And so we have in this particular situation, and we have for number 25, okay, so we have, again, we have for the lead-in, okay, so you have the principal, okay, so you have it $3,000. And again, we have R is equal to 10%. And again, we're going to express as a non-percent decimal. And for the time span, okay, so you have the time span is going to be for 6 years. Okay, now for what we have in the case of part A, okay, we have that N is equal to 12, since we are looking at monthly compounding. And we have for the formula, okay, so I'm going to have that A is equal to P times, okay, the quantity of 1 plus R over N to the N times T degree. Okay, so filling in the numbers. Okay, so we have P is at $3,000. We have times quantity. Okay, so you've got 1 plus R, we have at 0.10. N is going to be at 12. And for N times T, okay, so we have 12 times 6. And so for what we're going to have here, so you got 1.008. Okay, we have 3's that will repeat and follow. And if you just keep that base and take to the 72nd degree, okay, so you have $3,000. And for this number to the 72nd power, okay, so that's going to be a number a little bit over 1.8. Okay, so if you keep that display and multiply by $3,000, okay, and so for the future value, this will come in around 5,452.78. Okay, so this is for 10% after 6 years of monthly compounding. And again, now we've looked at cases where the more frequently the compounding is done at the same quoted percentage rate, the higher the balance is going to be. And we're going to anticipate a higher balance with going from monthly to continuous compounding. And we have with the continuous compounding, again, you have n approaching infinity, and this formula is going to change over to a is equal to p times the natural logarithmic base e raised to the r times t power. Okay. And so we have with p, again we have $3,000. We have for e to the r times t, so r is going to be at, again, at 0.1, and again t is going to be at 6. Okay, and so we have 3,000 times e to the 0.6 again, e is that natural logarithmic base number, that 2.718 figure. And for e to the 0.6, okay, in this one, that's going to be 1.8221188, and multiplying by $3,000. Okay, so for the monthly, again, you have the balance after 6 years to be at 5452.78, and with maxing out the frequency of the compounding to continuous, and we're going to have, and for this balance, okay, we're going to have a little bit higher, okay, in fact about, yeah, between $13 and $14 higher, where we had the balance to be at 54.66.36. And again, you have a little bit of a difference in this one. Okay, now as a backdrop to numbers 26 and 27, this will be in reference to what we will have regarding annuities. And so we'll be looking at these in terms of the minimum side as well as the maximum potential. And just a bit of a lesson that we have with annuities. Now, the compound interest formulas we have looked at in determining future value have been involving just one-time deposits. But let's say if you have like a plan of purchasing appliances or an automobile, and perhaps what would be, you know, the biggest purchase for some, like maybe a home or condominium or whatever, you might be looking at like a monthly, you know, purchase plan or investment plan, and this would be what we have in the case of annuities. And for what we have in the case of annuities. Okay, so we have for a recurring deposit. For a recurring deposit that is made n times a year, and we'll put stress on this at the end of each cycle, Cycle being like year, every 3 months, or quarter, or every month. Okay, so for a recurring deposit that is made n times a year at the end of each cycle into an account, that's going to draw interest. Also n times a year. So the frequency of the deposits and as well as the frequency of upon which interest is compounded, those will be the same. Same values, n times a year. Okay, so we're going to have for the future value, okay, what's going to be referred to as the annuity formula. And it's like going with the conservative side of things because you don't want to overestimate, so to speak. Okay, so we have in the case of annuities, you have the future value A is going to be equal to P. This is going to be the recurring deposited amount. And we have P times the quantity of 1 plus R over N. In fact, this is going to look like an amalgamated version of the compound interest formula concerning future value, and essentially it is. So you have P times, and you have in brackets, and then you have the quantity of 1 plus R over N to the N times T minus 1. And we have times N over R. So that's going to be your annuity formula. And let's say that looking at future value. Okay. So we have for the case P, let's say we have $300. So add the context here. So you have $300 deposit at the end of each month. Now we'll say that we have for the rate of interest. Okay, so you have rate of interest is at 6%. So about 0.06. And we'll say that for, again, so you're looking at the end of each month. Okay, so you have N is equal to 12. Okay, so again, you are looking at monthly compoundings as well as monthly deposits. And we'll say that we have for the time span. Okay, so this is going to be, we'll say we have 5 years. Okay, so you're looking at like $300 a month. Okay, multiply that by 12. Okay, so we're looking at like $3,600 a year for 5 years. So just the lump sum of the deposits, we're looking right at $18,000. And you're going to have this along with 6% interest compounded. And so for what we're going to have in terms of the future value, so we have with the numbers. Okay, so you have P, we have at $300. And we have times the quantity. Again, so we have 1 plus. For R over N, so you have 0.06. And we have N is at 12. And for the N times T, okay, so you have the 12 times 5. We have minus 1. We have times N over R, so N is at 12. And R again, we're going to have at 0.06. So about $300. Okay, now for what we have within the grouping symbols. Okay, so about 0.06 over 12 added to 1. So about like 1.005. And this will be to the 60th. You have minus 1. Now for 12 over 0.06, okay, this reduces to a whole number at 200. And we got 300. Again, now for 1.005 to the 60th, you have among the first digits, you have 1.34885. And we're still taking away 1. And we're getting very close, okay, to the final total here on this one. Okay, so we have for the difference, okay, so you have 0.34. Let's go ahead and write this out. 885.01525. Times 200. So once you multiply those numbers together, okay, so we're looking at 20,931.01. Okay, and so basically what has happened is that you have $18,000 put in, and you have like over $2,900 in interest that is added. Okay, so you have this particular lump sum if the individual or group or party is making investments or deposits at the end of each month. Okay, so this is kind of like the conservative side of monthly deposits of $300 into an account that draws 6% interest compounded monthly. Okay, this is for a 5-year total. Okay, now there is another added dimension, and I'm going to copy a lot of this. Okay, but it's going to be a lot of the same stuff. Let's say if someone theoretically is proactive about how early to put stuff into the account. Okay, so you have almost the same wording. Okay, but instead of having like at the end of each cycle, I put emphasis here. Say we have instead of at the end, say if I have at the start of each cycle. Okay, so what's going to happen here is that you're going to have the same formula. But you're going to have this added detail. We're going to have P times the quantity of 1 plus R over N. It's the same formula, but the difference this time is multiplying whatever the total is by the quantity of 1 plus R over N. Okay, and let's say if I had this same example here, and the difference this time is $300 deposited at the beginning of each month. In other words, like the first of each month. Okay. So again, I have this formula. And what's going to happen here is that for the 1 plus r over n, one plus r over n. Okay, so we have 1 plus, and r, again, we have 1 plus 0.06 over 12. And this will come out to 1.005. And guess what? I had already used the components from p 1 plus r over n to the n times t minus 1 times n over r. So if I considering that I've worked with the other stuff, but now throwing in multiplication by 1.005, so I got 1.005, okay, and what did I have before? That was this amount, 20,931.01. So the difference this time around, okay, it's going to be a little bit more, and in fact, okay, so for the future value, so the difference here, so if I put the deposits at the first of each month as opposed to the end of each month, okay, so we're looking at a little bit higher after 5 years. So we have the minimum, we have 20,931.01, and the theoretically maximum, this is going to be right at $21,035.67. Okay, so about a $104 or so difference. Okay, and where we have the annuities problems that come in, okay, from the review handout. Okay, so you have in the case of 26, I think what I'll do right here. Okay, so for what we have in the case of number 26, okay, we have Ray who plans to retire in 15 years. And it says that he contributes, okay, $1,000 to an IRA semi-annually. And guess what? The frequency of the compounding is done semi-annually at a rate of 10% interest. And now, we're looking at two scenarios here. And it's looking at what the minimum value of the IRA be when Ray retires. Okay, that is if he invests at the end of each 6-month cycle. And we're looking at the maximum if Ray retired and had invested at the start of each 6-month cycle. So have in the case of 26. Now we have in both scenarios. Okay, so we got the p-value at $1,000. And for the rate of interest, okay, so we have 10%. So 0.10, okay, and we have for the time span, okay, so Ray is looking at 15 years. And for the frequency, In other words, the frequency of the deposits, frequency of the compounding of interest. Okay, this is done on a semi-annual basis. Okay, and again we have in part A. Okay, so we're looking at the minimum value, and this is just the regular annuity formula. And to make this into the regular, again, I'm still looking at the minimum, so I'm going to take this part out. Okay, so we have on the minimum side. Okay, so we have so we got A is equal to, now we got P is at $1,000. And for 1 plus R over N, okay, so you have 1 plus R we have at 0.10, and N is going to be at 2. And for N times T, so we have 2 times 15. We got minus 1. And for times N over R, okay, so we have N is at 2. And we have R, again, we have at 0.10 from the 10%. Okay, so we got $1,000. And for what we have within the brackets, okay, so we got the quantity of what's going to be 1.05 to the 30th. Again, so you're looking at deposits twice a year, compounding twice a year for 15 years. Twice a year for 15 years, so you have 30 times. And 2 divided by 0.10, so that is going to be at 20. And for what we have concerning the activity regarding the compounding of interest, so you have 1.05 to the 30th, and that number is going to be a little over 4.3. Again, for this number, you're going to take away 1. And again, 2 divided by 0.10, that is going to be 20. And so you got $1,000, and the difference, I'll just go ahead and spell this out. So you have 3.321942,375. And we have times 20. So the minimum on Ray's IRA is going to be right at $66,438.85. So that's going to be the minimum. Okay, now for what we have in the case of the maximum, okay, and again, the maximum is going to be, okay, if he invests at the start of each 6-month cycle, okay, and again, just for the difference, okay, so you have this formula once again. Yeah, for part B. Okay, so we got the 66,438.85, and again, just the added item here, and this will be the 1 plus R over N So you have for 1 plus r over n, so it's going to be 0.1. N is at 2. So we have it 1.05. Okay, so what I have here is going to be 1.05. 5% more than the minimum. So you have 1.05 times 66, 438.85. And so theoretically, the maximum attainable balance, okay, is going to be like well over $3,300 higher. Where we're looking at $69,760. $79. Okay. And there is a bit of a domino effect because you might be looking at you're looking at with this pattern like investing at as close to the start of the year as possible and around the 1st of July, as opposed to waiting until the end of June and as close to the end of December, okay, for each year. So that pattern, okay, build up over 15 years, okay, it creates a bit of a difference, okay, of around $3,300. So that's where the dynamics kind of play out. So it amounts to a 5% difference total. Okay, now for what we have in 27, now you got the annuity formula, but you're kind of looking at it from a reverse perspective. And what I mean by reverse is that you know what the future value is. Now you're trying to determine how much has to be put in every cycle. And it says here that for a child born this year, a 4-year college education at a public university is projected to be roughly $170,000. And it says that assuming a 5% rate of return compounded monthly, about how much must be contributed to a college fund every month in order to have $170,000 in 18 years. Okay, so we're looking at a very big goal here. And we're using again the compound interest formula, but solving for p. So I'm solving for p, and it says to round up to the next penny in your answer. So normally, if you have like 34.4 cents, you're just going to round that up to 35. So you're not going to round down even if the third decimal place is 4 or lower. Okay, you're going to round to the next. Okay, so for what we have in the case of number 27, okay, so we're looking at least how much must be put in every month. Okay, so this is kind of like taking the reverse. Okay, so like you have, like somebody might have a, not just a college loan, but something like a mortgage amount, and it's that, well, I'm going to, kind of pay down the balance, in 15 years, maybe 20 years, about how much must I be paying out every month in order to get the whole thing paid off. So we have just for the items here. Okay, so you have the future value. It is that which is going to be $170,000. And for what we have, for the other items, okay, so we have the R. Okay, again, we have at 5%. So you have 0.05. Again, for the frequency of payments as well as the compounding of interest, okay, this is going to be done on a monthly basis. So n is equal to 12. And again, for the time span, okay, we're looking at 18 years. Okay. So again, we're looking at solving for P. Okay, so we got the numbers. Okay, so you have $170,000 is equal to P. And you have times the quantity. Okay, so you have 1 plus R over N. Okay, so you have 0.05 over 12. And for N times T, okay, so this is going to be 12 times 18. We have minus 1. And for N over R, okay, so I have times 12. And R, okay, so you have a 0.05. Okay, so for the activity we have going on, okay, within the brackets, so for 0.05 over 12 and add it to 1, so you're going to have like a 1.0041, and then we have repeating sixes to follow. And we take this sum and raise to the 216th power. Again, we have minus 1. Now 12 over 0.05, okay, that is going to reduce to 240. Okay, so you have P times the quantity. Now for this number to the 216th power, this number is a little bit under 2.5. Okay, and as we narrow it down, okay, so you have $170,000 is equal to P times, okay, and we have like 1.455008. Just keep that number multiplied by 240. Okay, and we have $170,000. Okay, and if I take the product of the difference and 240, and so you have 349 point, and write out all these digits. Okay, so you got this product times P. So you got 170 grand is equal to 349.2020215 times P. And if I divide this total by that 349.2 plus, it's going to result that for P, we have $486. You have 0.8242. And again, I'm stressing, okay, to the next penny. To the next penny. Okay, so that's going to be 83 cents. Not the nearest penny, but to the next penny. So we have in the case of the final result here, okay, so we're looking at monthly payments each right at $486.83. Okay, and so that would be the final results in this particular case. All right. Now, not that I'm a big fan of number crunching, and it did seem kind of frivolous with all these decimal places, but when it gets down to the nitty gritty with dollars and cents, and especially like 18 years worth of investments, and you're not left with much room for error, it can get kind of crossing over to where one crosses over into the micromanaging stage. All right, now going back to exponents and logarithms. Now we've dealt with exponential equations that share a common base, but let's say if the equations did not. Okay, so for exponential equations that have no common base, okay, and just kind of going back to our logarithmic properties, okay, because they are going to, in their own way, potentially re-enter the scene. Again, we had like a base A logarithm of a to the x is equal to x. Again, we have a base A logarithm of m to the r is equal to r times, okay, the base A logarithm of m. And also we have, just going back to the change of base formula. So you have the base A logarithm of m. Again, you have, say, is equal to the natural logarithm of m over the natural logarithm of a. And again, you can take the ratio and just have, in terms of base 10 logarithms, where you have base 10 logarithm of m over the base 10 logarithm of a. Okay, all right. And now, okay, so just, you'll see these very likely in some way, shape, or form for this type of set of equations. Okay, so if we have, let's say, looking at solving for x. Okay, and we'll say that we have, if we're looking at solving for x, we'll say we have 4 to the x is equal to 39. So you got 4 to the x is equal to 39. Now we can just have sort of an eyeball estimate about what x is going to be. And again, you have like, so you have like 4 to the first is equal to 4. 4 squared is equal to 16. And we've got 4 cubed is equal to 64. And if you notice, okay, you have somewhere in between 16 and 64, you got 39. So you got 4 to the 2 point something is equal to 39. Okay, so in terms of looking at solving for x, again, so we have 4 to the x is equal to 39. Okay, now what I can do here is I can convert the left-hand side to x with this property. So what I can do to knock out the 4 here, I can take a base 4 logarithm of both sides. So I got a base 4 logarithm of 4 to the x. So these 4's will go out. Left hand side becomes x. So now we've got x is equal to the base 4 logarithm of 39. Now, in many typical scientific calculators, you're not going to have the base 4 logarithm, but you do have natural and base 10 logarithms. So here I can perform the change of base formula, whereupon I can say that I have x is equal to the base 4 logarithm of 39, and I can apply either natural or base 10 logarithms. So I have a at 4, m at 39. And so if I use natural log, so I have that of 39 over the natural logarithm of 4. And so for your value x in this particular case, say to about the nearest 4 decimal places, this will come out to right at 2.6427. So if I took 4 to that degree, it's going to be very close to 39. And again, I'm just limiting this to the first 4 decimal places. It might be like 38 point something, 38.999, or 39.00 something. But again, you have to the nearest 4 decimal places. This is going to be the value for x. Now, if I have, let's say, for the variable x, let's say if I have the exponential base to be greater than the constant to which the exponential expression will be set equal. Okay. So we got here fourth root of 39. Fourth root of 39. No, I know what you're saying. Those are different items. It's not going to be the same thing. Okay, so you have like 100 to the x is equal to 15. Okay, so you have in this one. Okay, so for this figure, okay, so you have like say like 100. Now 100 is a non-zero number, and a non-zero number to the 0 power is equal to 1. Now we got 100 to the first is equal to 100. So that means that you're going to have like 100 to a positive number, okay, that is less than 1, so it's going to be like 0 point something is equal to 15. Okay, so you got 100 to the x is equal to 15, so your power of x is going to be like 0 point something. So you got 100 to the x is equal to 15, and if I reapply, let's say the base a logarithm, okay, where a is going to be at 100, so if I, just like what I did with 4 to the x, if I convert 100 to the x into x, so I'll be taking this rather large base logarithm, where I have a base 100 logarithm of 100 to the x is equal to the base 100 logarithm of 15. So we have left-hand side. So this will go to x. So I have x is equal to the base 100 logarithm of 15. And if I were to determine, okay, with the change of base formula, okay, so I want to apply this time, I can go with ln once again, but I'm just going to go with log. So I have a base 10 logarithm, 15, where m is represented by 15, over base b logarithm of a, which we have represented by the base 10 logarithm of 100. And if I were to take the ratio in this one, it's going to turn out that for x, okay, say to about the nearest 3 decimal places, this is going to be right at 0.588. Okay, so 100 to right at 0.588. Okay, that is going to be equal to 15. All right. Now, if we have, let's say, some situations here, and let's say that, tell you what, just a couple of quick problems, and there is one other item I do want to mention. And let's say that in terms of solving for x, let's see what we get first of all for 5 to the x is equal to 77. And also, let's see what we get for 12 to the x is equal to 4. Okay, so just the next few moments. Let's see what we get for x, and 5 to the x is equal to 77, and 12 to the x is equal to 4, and say take to about the nearest 3 decimal places. Okay, just for what we have regarding 5 to the x is equal to 77. If you're still working on these items, that's fine. Now for 77, okay, now we have like 5 squared is 25. Now 5 cubed, or 5 times 5 times 5, is going to be 125. And 77 is a number that falls between 25 and 125. So we would anticipate that the exponent, or the power to which 5 is raised, is going to be somewhere greater than 2 and less than 3. Whereas in the case of 12 to the x is equal to 4. Now again, 12 to the 0 is equal to 1. And 12 to the first is equal to 12. And 4 is between 1 and 12. So one would anticipate that the power to which 12 is raised is going to be a number that is positive but less than 1. And so just looking at what we have in the setup. Now for 5 to the x is equal to 77. And if I go with the approach of converting 5 to the x to x, so I can take the base 5 logarithm for both sides. Okay, so left-hand side, so we have x is equal to the base 5 logarithm of 77. And again, I can apply either natural or base 10 logarithms. Okay, so the change of base, okay, we'll go with ln. So you have the natural logarithm of 77 all over the natural logarithm of 5, and to about the nearest 3 decimal places. Okay, we have x will come out to about 2.699. Okay, so the value of x, or the exponent, does come out to be greater than 2 and less than 3. So you have very close to 2.7 in this instance. Now for 12 to the x is equal to 4. Okay, so if I go just like what I did with 5 to the x, converting to x, I can take logarithm with the base that matches 12. So we have a base 12 logarithm that I can apply to both ends. So I have the base 12 logarithm of 12 to the x is equal to the base 12 logarithm of 4. So the left-hand side becomes x And we have the x equal to the base 12 logarithm of 4. And I can use the change the base formula, and I can reapply natural logarithms in the ratio, but it'll work just as well if I go with the base 10 logarithm. Doesn't matter which one, it's going to be the same effect. And if I take the natural or base 10 logarithm of 4 divided by that of 12, and to about the nearest 3 decimal places, again, so we have x is going to be about 0.558. Okay, and if you notice, okay, so far we have had the exponent or the power to be on one side of the equation. Now, for what we have, if you happen to have the exponent on both sides, I'll give you a case here, and I'm going to refer back to, once again, these formulas. Okay, now let's say that if I'm looking at solving for x, I'm just going to put this over here. And this is kind of like a situation that you might encounter in ALEKS, okay? Because you might have an exponential equation that's going to have no common base, but where the variable x will be in the power position on both sides of the equation. So if I'm looking at solving for x to the nearest 4 decimal places, okay, and let's say that, okay, we have 18 to the x plus 2 is equal to 22 raised to the x minus 1. And believe me, I like the problems a lot more when you have just the exponent or the variable on one side of the equation. Okay, and for this one now, it's not going to be an advantage to take base 18 logarithms or base 22 logarithms. So as a bit of a compromise for this problem, you can take, since we've had natural or base 10 logarithms in the change of base formula, I can take natural or base 10 logarithms on both sides. And I can understand why one might be inclined to take the base 18 logarithm, and there would be a vantage point if I did not have the exponent in x to be applied to 22 as well. Okay, so if I take ln or log, and what I'm going to do here, I'll go with natural logarithms. So I have the natural logarithm of 18 to the x plus 2 is equal to the natural logarithm of 22 raised to the x minus 1. Okay, and one might ask, okay, after this, okay, what is going to come next? Okay, and I'll just write this step down one more time. Okay, so got log or ln, either approach works. And next, okay, you got this property where you have going from exponent to coefficient. And guess what? That's what I'm going to do with x plus 2 as well as x minus 1. And both x and 2 will be multiplying the natural log of 18. So I want to put what I have here in parentheses. So I've got x plus 2 in parentheses, or x plus 2 quantity, times the natural logarithm of 18 is equal to, and likewise with x minus 1, putting that also in parentheses. So I have x minus 1 quantity times the natural logarithm of 22. Okay, now what we're going to do here is that we're going to split up. So I'm going to multiply natural logarithm of 18 by x plus 2. So we have the formation of x times the natural logarithm of 18 plus 2 times the natural logarithm of 18. And then to the right, we have x over the natural logarithm of 22. And we have minus 1 times the natural logarithm of 22. Okay. If you notice, we have 4 natural logarithmic terms. And we have 2 in x and 2 as just standalone logarithmic terms. And what I'm going to do here is I'm going to gather together the x terms. So what I'm going to do simultaneously, okay, is that I'm going to gather together the x terms, and I'll just take x times the natural log of 22 and deduct from both sides. So I have x terms on the left, and what I will do at the same time is subtract 2 times the natural log of 18 . So for what this comes down to, okay, so I have x times the natural logarithm of 18 minus x times the natural logarithm of 22. And then to the right, I have negative logarithmic terms. So I have minus the natural logarithm of 22 minus 2 times the natural logarithm of 18. Okay, and I'm still solving for x, but I got a couple of x terms. And okay, so to make this into one x expression, what I can do here for this difference is to factor out x. So if I factor out x from this difference, so I'm going to have x times the difference between the natural log of 18 and the natural logarithm of 22. Okay. And for what we have here, okay, so once I get it down to what we have in terms of x, okay, so I'm going to divide this difference here by the natural log of 18 minus the natural logarithm of 22 . Okay, all right, so we have here, if I were to put this in calculator notation, all right, so I got this difference here. So let me put it this way: if I have a ratio between differences for the top and the bottom parts, I want to be able to use parentheses. So using a bit of calculator notation, so we have like the negative of the natural logarithm of 22 minus 2 times the natural logarithm of 18. And so I'm going to do a little bit of color coding here. Just put that in blue. Okay. So got the difference. Okay, so you have the negative, the natural logarithm of 22 minus 2 times the natural logarithm of 18. Close out for 18, close out for the difference. And we have here, we have all over, and we have in parentheses. We have the natural logarithm of 18 minus the natural logarithm of 22. Okay, so as you enter this as one segment, so you've got in the numerator, we want this in parentheses, you got division, and what's in the denominator, okay, I want in parentheses. And for what we have in the case of x to about the nearest 4 decimal places, okay, so you have 44.2107.